Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. In this lecture, we are going to discuss one more question on two-dimensional random variables. This question was asked in GTU Winter 2020 examination. If two random variables x and y have the joint density fxy equal to k times x plus y square when x is in between 0 and 1 and y is in between 0 and 1 and fxy equal to 0 elsewhere. So if this fxy is the joint PDF of two random variables x and y, then we have to find out value of this constant k, and also we are asked to find out the mean of the conditional density of the first random variable when the second takes on the value 0.5. That means we have to find the mean of the conditional density f1x given 0.5, where f1x is the marginal probability density of x. So far we have used this type of notations for marginal densities of x and y. This was the notation for marginal probability density of random variable x, and we have used this notation for marginal PDF of random variable y. So instead of this notation in this question, they have used this notation f1x. So f1x is the notation for marginal density of random variable x. Similarly, marginal density of random variable y can be denoted by f2y. So here random variable 1 stands for x and random variable 2 stands for the random variable y. And also we have defined conditional probability density in earlier lectures. There we have used this type of notation. We have used this notation for the conditional density of random variable x given y. We have used this notation f of x by y. This is the notation for conditional probability density function of the random variable x given that y equal to small y. And in this question, instead of using this notation, they have used this notation for conditional density function of x. So instead of x, they have used 1, and here they have used x by y. And here we have to find out for particular value of y, which is 0.5. So this f1 x by y is the same as this, but in this question we have to understand these different notations. So these are the different notations for the same thing. Instead of conditional density of x, they are using conditional density of first random variable capital X, which is denoted by 1. And we have defined this conditional density function in earlier lectures. If you are watching this lecture first time, and if you have not watched previous lectures on two-dimensional random variables, then I suggest you to watch those lectures first. So this conditional density of x given that y equal to y is defined as ratio of joint density divided by marginal density of y. So instead of capital Y, we will use f2y. Okay, we have to use these notations which are given in the question. So sometimes they are using this type of notations, sometimes they are using these notations. So we must be familiar about different notations for the same thing. So here first we have to find out value of k, so that this fxy is a joint probability density function, or it is given that fxy is a joint probability density function. So we have to find out value of k, and once we find out value of k, we will be able to decide this conditional density function of random variable x given that y equal to small y. For that we have to decide marginal density of random variable y or marginal density of second random variable. So first we find out value of k. For that we use the property of joint PDF. We know that if f is the joint density of bivariate random variable x, y, then double integral of this joint density function with respect to x, y over the given range must be equal to 1. So using this property we will be able to decide value of k. So first we find out value of k. So we can write that fxy is joint PDF. Therefore we must have double integral of fxy with respect to xy. Double integral is considered over all possible values of x and y. So this must be equal to 1. Now we concentrate on the definition of joint PDF. It is given that joint PDF is non-zero if x and y lies between 0 and 1 and it is 0 otherwise. So we can replace these limits by limits from 0 to 1, because outside 0 to 1 function is 0 and between 0 and 1 value of function is k times x plus y square. So here we replace fxy by k times x plus y square. First we integrate with respect to x, and while integrating with respect to x we consider y as constant, and then we will integrate with respect to y, and this must be equal to 1. Now here k is independent of x and y, therefore I can take k outside the double integral. Here we consider y as constant and we integrate x plus y square with respect to x. So integral of x is x square by 2 plus y square is constant, and integral of 1 with respect to x is x, and limits of x are from 0 to 1, and this must be equal to 1. Therefore k times 0 to 1, first we take x equal to 1, so we have 1 by 2, 1 square is 1 by 2 plus y square into 1, and lower limit is 0, so we will have, if we put x equal to 0, then we have 0 for the lower limit. So we have 1/2 plus y square dy equal to 1. So therefore now we integrate with respect to y, so we have y by 2 plus y cube divided by 3. Limits are from y equal to 0 to 1, and this is equal to 1. So therefore k times here first we put y equal to 1, so we have 1/2 plus 1 by 3, and for lower limit it is 0, so this is equal to 1. So therefore k times this we can rewrite as 3 plus 2 divided by 2 into 3, that is 6. So this is k times 5 by 6 equal to 1, and therefore value of k is 6 by 5. So we have completed first part of the question. It is given that f is joint density of bivariate random variable x, y. Then we have to find out value of k. So now we can write down value of k in the joint density function of given bivariate random variable. Okay, so therefore the joint PDF of random variables x and y is fxy equal to k times x plus y square k is 6 by 5 and 0. This is for 0 less than x less than 1, 0 less than y less than 1, and outside these values of x and y, value of joint PDF is 0. So we have taken k equal to 6 by 5 here, and we obtain the joint PDF of bivariate random variable. So we have obtained this unknown constant. Now we have to find out the mean of conditional density of the first random variable when the second takes on the value 0.5. So as we define, this is the definition for conditional density of random variable x given that y equal to y, and this we have to find out for y equal to 0.5. So first we write down this definition and then we calculate. So now by definition, conditional density of random variable x given that y equal to y, this is going to be value of joint density divided by marginal density of random variable y. Now here we have given particular value. It is given that y is 0.5. So we take y equal to 0.5. So therefore f1, that is conditional density of random variable x given that y equal to 0.5, will be equal to value of joint density at x comma 0.5 divided by marginal density of y at 0.5. So we are already having this we are already having joint density. So this we can obtain from joint density by taking y equal to 0.5. So we first have to decide marginal density of second random variable y. So first we find out marginal density of second random variable, that is y. So now the marginal density of y, which we consider as second random variable in this question, is, it is denoted by f2y. We have used this notation for marginal density. In this question we are using this notation for marginal density of y. So we know that by definition we have to integrate joint density with respect to x over all possible values of x, and here we will consider y as constant. Now we are given that if x is outside 0 and 1, value of joint density is 0, and for x between 0 and 1, joint density is 6 by 5 times x plus y square. So we are using this definition for 0 less than x less than 1, fxy is 6 by 5 times x plus y square. So now we can integrate this easily, but we will take care that here integral is with respect to x, so we will consider y as constant, and we take this 6 by 5 outside. We can write one more step, integral from 0 to 1 x plus y square. Integration is with respect to x, y will be considered as constant. So integral of x is x square by 2, y is constant, so y square is also constant, and integral of dx is x, and these are the limits of x. So we consider x from 0 to 1. So if we take x equal to 1, we have 1 by 2 plus y square. So this is the marginal density of random variable y, and this is when y is in between 0 and 1, and if y is not in between 0 and 1, marginal density of y will be 0. Now we are interested in the marginal density of y at 0.5, so we substitute y equal to 0.5 and we obtain this is going to be 1 by 2 plus square of 0.5. So we can simplify this. This is 6 by 5 plus 1 by 2 plus 0.5 into 0.5, that is 0.25. And we can further simplify this. We can take 2 LCM. So we have 1 plus 0.25 into 2, that is 0.25 into 2, that is going to be 0.5 divided by 2. So we can further simplify this. This is going to be 3 by 5. This is going to be 1.5. And we can further simplify this by writing 1.5 as 15 by 10. And if we observe, we obtain 9 by 10. So this is the value of marginal density of random variable y at 0.5 that we require. Okay, fine. So we have obtained marginal density function of second random variable y at 0.5, which is 9 by 10. Now we come back for this equation. We require conditional density of first random variable x when y takes the value 0.5. So this we have obtained. This we can obtain by taking y equal to 0.5 in the formula for this joint density function. So this we can obtain by taking y equal to 0.5. So now we come back with that formula again. So now we are interested in conditional density of random variable x given that y is 0.5. So this is by definition value of joint density at point x comma 0.5 divided by value of marginal density at 0.5. Now this is going to be f of x comma 0.5 that we will obtain from the formula of joint density. So here we obtain we take y equal to 0.5 and we will obtain 6 by 5 times x plus square of 0.5. So we write that 6 by 5 times x plus square of 0.5, that is value of y, and divided by value of marginal density at 0.5, which is 9 by 10. So that we write here. So now we have to simplify all these things. I can rewrite this as 6 by 5 times 10 by 9, and this is going to be x plus 0.5 square, that is 0.25. So here we can cancel out 5, here we can cancel out 3. So we have 4 by 3 times x plus 0.25, and I can multiply this bracket by 4. So I have 4x plus 0.25 times 4, which is going to be 1. So this is the conditional density of random variable capital X given that random variable y takes the value 0.5, and this is non-zero for 0 less than x less than 1, and it will be 0 outside this range of x. Now we are asked to find out mean of this conditional density. So mean of conditional density f1 x given 0.5 is equal to, we have to take integral of this density function with multiplication by x x times f1 of x by 0.5 with respect to x, and this is defined, or this is non-zero when x lies between 0 and 1. So here we consider integral from 0 to 1, and this density function is 0 outside this interval. Therefore we are considering limits of integration from 0 to 1. So here we consider 0 to 1. Value of this density function is 4x plus 1 divided by 3. So 4x plus 1 divided by 3 integral with respect to x. So this is going to be, we can take 1 by 3 outside and we multiply 4x plus 1 by x. So we have 4x square plus x integral with respect to x. Now this is easy to integrate. 4 as it is, integral of x square is x cube by 3 plus integral of x is x square by 2. X is from 0 to 1. So for upper limit we will have non-zero contribution. We take x equal to 1 and we obtain 4 by 3 plus 1 by 2, and contribution for lower limit will be 0. Now if we take LCM, we have 6 here and we have 4 into 2, 8 plus 3. So finally we obtain 11 by 18. So this is the mean of conditional density. Mean of conditional density f1 of x given 0.5 is 11 by 18. So we were asked to find out this quantity, mean of conditional density. Okay, so in this way we can easily find out this type of solutions of this type of questions, but we have to remember all these formulas appropriately. So here we have used almost all the formulas. We have used the property of joint density function to find out value of k. We have used this property that if f is joint density function, then this integral must be equal to 1. Also we have used the definition of marginal density. We know that marginal density of y is given by integral of joint density with respect to x over all possible values of x, and this we have denoted by f2y. Also we have used the definition of conditional density of x given y equal to y. We have used this definition, fxy divided by marginal density of y. So instead of this notation, they have used this notation, f1 of x given y, and instead of this denominator, instead of this notation for marginal density of y, they have used this notation, f2.5. And this we have calculated for particular value of y, which is given as 0.5. And finally, using the definition of expectation, we obtain the mean of this density, which we are using this notation. We have used this notation for mean or expected value of conditional density, and using this we are able to find out mean of conditional density. Integral with respect to x, we have to integrate over all possible values of x. So this is all about this lecture. I hope you like it. This is very important question. It was asked in this winter 2020 examination of GTU. So I hope you like this lecture. Thank you very much.